Hello everybody, Mr. Hasty here again. Today we're going to be talking about modeling collisions using the conservation of energy. So we already did some of this using the conservation of momentum. And the formula for momentum, if you remember, is mass times velocity. We're going to use that a lot. And we're also going to talk about the kinetic energy. So one of the interesting things about this is that momentum is always conserved, but energy is not always conserved in the way we want it to be. So even though energy is always conserved within a system, some of that energy could turn into other forms of energy that we don't want. And we'll talk about that specifically as it happens. So the key component here is that momentum is always going to be conserved. Kinetic energy won't always, but total energy will. So we're going to look at 4 cases here. In every one of these cases, we're going to have ball A striking ball B. Each of the balls is going to be 1 kilogram. And initially, ball A is going to be traveling at 1 meter per second. And ball B is going to be at rest. So before we go into that, let's talk about the initial kinetic energy and the initial momentum of this system. So the momentum of ball A is mass times velocity, 1 kilogram times 1 meter per second. We have a momentum for A of 1 kilogram meter per second. And the momentum for B, because it has 0 velocity, is 0. So our total momentum is 1 for our system. And that always has to be true. No matter what example I come up with, the momentum has to be conserved. Now, our kinetic energy, I'm going to here, the initial kinetic energy of A is 1/2 times 1 times 1 squared, which is 1/2. And our kinetic energy of B is 0 because it has 0 velocity. So our total kinetic energy of this system is 1/2, or 0.5 joules. So case 1. Case 1 is where when they strike, A stops. And B, now if A stops, B has to pick up all that momentum. So that means that B has to have a momentum of 1. Since B is a 1 kilogram object, it's going to have a 1 meter per second velocity. Remember, momentum has to be conserved. So if we have 1 kilogram meter per second initially, then if ball A is stopped at 0, ball B has to take on all the momentum. So that's very nice. Let's talk about the kinetic energy now. So after everything's done, the kinetic energy of A is 0 because it has no velocity. The kinetic energy of B is 1/2 because it has a 1 kilogram mass and 1 meter per second. So that means that we have the same amount of kinetic energy before the collision as we did after the collision. So the term we're going to use for that is elastic. That is called an elastic collision. Now, case 2 is what if the 2 balls end up with the same velocity? Now, this oftentimes is envisioned as things getting linked together or stuck together through the collision. So if ball A and ball B get linked together, remember the momentum has to be conserved. So before we had a momentum of 1, so this system has to have a momentum of 1. Now notice that we doubled the mass though. So we have 2 kilograms worth of material, so our velocity would have to be half as much. We're going to have to come out at 0.50 meters per second. So in that situation, we end up with the same momentum, but our kinetic energy is going to be different. The kinetic energy of A is 1/2 times the mass times the velocity. Well, 1/2 times 1 times the velocity of 1/2 squared is going to be 1/8. And the kinetic energy of B is going to be the same. So we actually end up with a total kinetic energy of 1/4, which is less than what we started with. This is called a perfectly inelastic system. Perfectly inelastic system. So in this situation, kinetic energy was not conserved. So that means it had to transfer into another form of energy. Where could that go? Well, if two things are in contact, we could have the vibration of those two things is motion that we're not considering as they hit each other. They could transfer into heat from the friction surfaces in contact. And any other manner of energy that would be appropriate to that situation. So case 3. What if A just slows down a bit? So what if A goes from having a 1.00 meter per second to a 0.4 meter per second? And that means that if we want to conserve momentum here, they have to have a momentum of 1. So B would have to have 0.6 meters per second. So this would be a situation where A hits B, A keeps moving a little bit, B ends up picking up most of the velocity. So after this, the kinetic energy of A would be 1/2 times 1 times 0.4 squared, which would be 0.08, and the kinetic energy of B is equal to 0.18, which gives us a total kinetic energy of 0.26. So in a perfectly elastic situation, remember our kinetic energy in a perfectly elastic situation was 0.5 joules. When we had case 2, we went down to 0.25. And in this situation, we have 0.26. So we kind of see that there's like this range of potential kinetic energies that occur. And the kinetic energy be lost in a similar way through vibration, things like that. This is just referred to as an inelastic. It's not perfectly inelastic. Perfectly inelastic implies that they end up with the same velocity. But if they don't end up with the same velocity, it would just be called inelastic. And finally, the last case. What if something bounces backwards? So what if A bounces off ball B? And A is going, now we have to keep signs here. What if A is going at negative 0.2 meters per second? If we want to conserve momentum, that means that ball B would have to be going at 1.2 meters per second. Well, our kinetic energy of A then is going to be, now energy is not going to care about our sign because of the squaring in the process. So I get 0.02, and my kinetic energy of B is going to be 0.72. So we get 0.74 total energy, which is more energy than we started with. So what does that mean? It means there had to be energy somewhere in this system in a stored form. Most commonly, these type of collisions occur when some sort of spring mechanism is activated. So there's some stored potential elastic energy in some form that is released upon the impact. And this is referred to as a super elastic collision. So super elastic. So let's give these terms elastic and inelastic a more formal definition. So elastic means that is defined to mean a collision where kinetic energy is conserved. And inelastic is a collision where kinetic energy decreases. Super elastic. Now, we'll talk about perfectly inelastic in a second. Super elastic is pretty much where kinetic energy increases. So if kinetic energy is conserved, it's called elastic. If it decreases, it's inelastic. And if it increases, it's super elastic. Now, perfectly inelastic is kind of like the lowest you could possibly go, right? In a given situation. So that just kind of happens when usually they end up splitting the momentum equally between them. So if we want to know specifically what perfectly inelastic is they share equally. And it creates a low bound for how much energy, kinetic energy, we can lose within a system. All right, let's move on to a couple examples. Example 1, a car with a mass of 1,250 kilograms. So let's kind of diagram this as we go. 1,250. It's traveling at 18.0 meters per second. Collides with a car with a mass of 1,450. Is traveling at 6.0 meters per second. In the same direction. The cars become interlocked. Okay, so that means that we're going to have a situation after this is done. So this is our before picture, and our after picture is going to have a linked system with both vehicles traveling at the same velocity. So what is the final velocity of the cars? So part A, we don't really need our discussion of kinetic energy here. We can handle this with the conservation momentum. So the momentum of the system before has to be equal to the momentum of the system after. So the momentum of the system before is the momentum of the two cars added together. So the momentum of car A plus the momentum of car B has to be equal to the momentum of A plus B when they lock together. So the momentum of A can be calculated as 1,250 times 18.0. Car B can be 1,450 times 6.0. And that's going to be equal to the combined mass of those two vehicles. We got to be careful we don't lose sig figs here, but is essentially 1,250 plus 1,450 times the velocity of that system. So we'll just call that V final. Now, algebraically, we just solve for V final, and we will get, let's see, two sig figs, because 6.0 meters per second would be 12 meters per second. So So let's briefly see if that makes sense. We had 18 meters per second and 6 meters per second. So we imagine that the final velocity be somewhere in between there. And we could check it by looking at the kinetic energies, but we're going to do that in part B. How much does the kinetic energy, how much change in kinetic energy was there? So what we have to do is we have to look at the kinetic energy before and the kinetic energy after. So the kinetic energy before is going to be the kinetic energy of A plus the kinetic energy of B. And then we're going to compare that to the kinetic energy of A plus B, the final, when they are linked. So we get 1/2 times 1250 times the velocity squared, 18.0 squared, plus 1/2, and I'm just using the 1/2 mv squared, 1450 times 6.0 squared, and we get 228,600 joules. Now, in this situation, our mass is going to be the sum of the two masses because they link together. And we have to use their final velocity. Now, again, this is a rounded value, so we actually need to go back and use the original value, which was 11.555, and so on. Now, how would I enter that in the calculator? I'm just going to put enough 5s to where our level of precision is going to account for it. I get 180,267, and that's going to keep us in sig figs. Remember, we're limited here to 2 sig figs in the end. So once we do the subtraction here, that will be rounded. I get about 48,000 joules. So we lost about 48,000 joules in that situation of kinetic energy, I should say. But really, you never lose energy. So part C, where did the energy go? So 3 sources. Vibration, which is motion that we don't really care for when we analyze systems typically. Heat from frictional contact, and deformation. When two things collide, a lot of times there's deforming of the material and structure, and that is basically energy that has to be spent manipulating that object and is not spent becoming kinetic energy. All right, we're going to look at one more example. Okay. So last example here. Ball A with a mass of 2 kilograms. So ball A has a mass of 2 kilograms. In ball B is at rest, which means 0 meters per second. The first ball is traveling at 6 meters per second. Okay. Determine the type of collision after they strike. Okay, so when we're determining the type of collision, we're going to assume that our momentum is conserved because it should have been. But what we're going to be doing is checking out the kinetic energy before and after, and then comparing that to our definitions of different types. So let's work out what the kinetic energy is at the beginning, because every one of these situations has the same kinetic energy at the beginning. It's 1/2 mv squared. The mass is 2 of the first ball, and its velocity is 6.00 squared. The kinetic energy of the second ball is going to be 0 because it has a velocity of 0, so we're just going to work out the first ball. So we have 36 joules of kinetic energy to start with. So now what we can do is we can compare how much kinetic energy is in the end scenario to that, and that'll give us, let's label this initial, and that'll give us an access to our definition. So in this situation, the kinetic energy final It says the ball A is stationary. Okay, so it has 0 kinetic energy. And ball B travels at 6 meters per second. So mass of 2, velocity of 6 meters per second, and we're going to get 36 joules. So in this case, the kinetic energy is fully conserved, so that means that this is called an elastic collision. Part B. All right, so in this situation, ball A and B traveled together at 3.00 meters per second. So that traveling together is oftentimes an indicator of a perfectly inelastic collision. So at the end, they're together, so we can do it as one object. They have a total mass of 4 because it's 2 plus 2. And they are traveling at 3 meters per second. Square that. Work that out, we get 18 joules. That is less, and because they linked up, I'm going to say this is a perfectly inelastic collision. Usually if it comes out about half as much and they join together, it's perfectly inelastic. All right, part C. Ball A is traveling at 2.50 meters per second. Ball B is traveling at 3.50 meters per second. Okay, so ball A has a mass of 2 at 2.5, and ball B has a mass of 2 at 3.5. So let's work that out and see what we get here. And we end up with 18.5. So given that we called this one perfectly inelastic, and notice that the kinetic energy is between what we started with and our perfectly inelastic situation, I'm just going to call this one inelastic, not perfectly inelastic, because they didn't end up at the same velocity. I'm just going to call it inelastic. Part D. Ball A is traveling at 0.50 meters per second in the opposite direction. So we need to call that negative. It's not going to matter really for our calculation because we're going to square it, but it's important that we keep track of these things. And ball B is traveling at 6.5, which is faster. I'm going to bet you money this is super elastic. So when we do this, we get 42.5 joules. And so that is definitely super elastic. Now, we're going to talk about some things that you're going to see here. And then we're going to talk about how you can't always just use that instinct. So basically, in part A, now notice that both these balls have the same mass. And that's a big deal because it leads to this set of reasoning. If they have the same mass, we can do a lot of shortcuts. For instance, noticing that in part A, all the velocity transferred to the other ball would let us know that it's elastic. But what if the other ball was double the mass? Then it wouldn't be half of the velocity then. It would be a factor of that by the square. So the situations when the masses are equal are pretty straightforward. If they link up and go at the same speed, it's perfectly inelastic. If they end up transferring all the speed, it's elastic. If they both slow, if one of them slows down as the other one speeds up, that's inelastic. And if they rebound or kind of ricochet off each other, if the total speeds coming out of that are higher than the speeds going in, like 6.5, then you're going to have a super elastic. But once we start messing with the masses, you can't just make those assumptions. All right. That's it for today. See you guys next time.